Hi.
Hey,
Hi, Fancy.
hey, how are you?
Fine. So let me introduce you before you jump in. So our next speaker is Franziska Meier. She received her PhD from USC, and she was also a researcher at Max Planck Institute for Intelligent Systems, as well as a postdoctoral researcher with Dieter Fox at University of Washington, Seattle. And she's going to talk today about learning loss functions for fast adaptation of robot dynamics. She's currently researching, leading the research efforts in robotics at Facebook. And yeah, very excited to hear it.
Hi, thanks for inviting me. I'm super excited to be talking at your workshop. I have been thinking a lot about action spaces as well, like, what we should be using here, just maybe from a different perspective. So I'm excited to share my perspective today, but also I have questions for you and I would love to hear your thoughts. So, okay. Oops. Yes, let me find my pointer here. Okay. So I do robotics and machine learning, and I focus mostly on manipulation. I think about when I think about robotics, about robots, I think about all of these tasks that they somehow should be able to do. And it's not just the amount of different skills that I think about, but also just all the possible variations that these tasks could appear in, right? Like let's say take the example of watering a plant here. Once a robot has learned to water this one plant here, it should be able to water other plants as well. So this is where I'm coming from. That's my mindset. I'm nowhere close to this. It's just kind of the motivation. When I think about how we get there, I really think we should be learning representations that enable fast learning of new skills or adaptation to novel settings. So I don't believe in this. We have one training set and we'll be able to learn everything the robot needs to know a priori, and then we send the robot out into the world. No, I think we need to learn representations that enable the robot to learn new skills fast or adapt to novel settings. And specifically today, I'm going to focus on this adaptation to novel settings, how we could get there. I want to focus this talk a little bit, so I'm just going to talk about pick and place now, just because it's easy to illustrate some of the thoughts I have with this problem. So let's say you have a robot that is supposed to pick and place all of these objects and put them on the table or from the table back into the shelf. This is kind of the controller mindset I have. I have a KUKA arm here. I assume there is a policy that is giving some action. And since you're talking about action spaces a lot, I believe most of you think about these kind of action spaces here and effector positions, joint positions, maybe impedances, forces that you want to control. The mindset I have is that there is a controller underneath all of this that actually does send torque. So I believe in torque control because it is one way of enabling safe interaction with humans and the environment. So these controllers, they take these actions and then compute the final command that is sent to the robot. Other people will tell me this is not even low enough. There's yet another layer lower, but this is where I draw the line, basically, at torques and efforts. Yes, okay. So I want to just quickly illustrate what happens when you have such a controller set up. You have tuned it for the robot to be compliant, but also track a trajectory that you see here. So this is what my robot does in simulation when I ask it to track this green line. It's very light only. It does perfectly. It's also simulation. So there's, this should be expected. But now this robot in simulation picks up an object and it's supposed to follow the same line the robot, the controller is not aware of this object. And again, the controller has been tuned for the free space motion. And you see that the arm is dropping, right? It's supposed to track the same line, and it's just not compensating for the mass of the object. And so it drops. And this is something I've been thinking about a lot. How do we compensate for these unmodeled dynamics? And I think what I see a lot in the community happening right now is that this is tried to be compensated up here. And that's a question I will have for the rest of the community. I don't fully understand why this might make sense. To me, it should be compensated down here, right? That's how I grew up, basically. Yes, okay. Here's a slide of all kind of different approaches I've tried to compensate these dynamics with. The point here is not for me to explain all of this, it's just I thought about a lot. And to me, it was always important that these algorithms can perform these dynamics predictions. So this is learning of the dynamics model for the controller. To compensate for these unmodeled dynamics, they need to be fast enough to run at that controller frequency. And then I thought about simple models and complex, so just be adaptive or learning a fully global model. And after a few years of doing this and getting back to this picture where I just really want to learn how to pick and place these objects, I've started to wonder, should I really try to learn all of these dynamics models? Should I really try to learn this one global dynamics model, or should I learn how to adapt? And this is where I'm right now. To me, it seems impossible to learn a model for each. Let's even constrain it to rigid or non-rigid body, right? It seems just impossible for me to learn a model for each rigid or non-rigid body a priori. But it does seem feasible to learn how to correct for deviations from expected sensor signals. So as you're trying to move, as the robot is trying to move, it knows it's deviating from what it's supposed to do, because we do have joint measurements, at least in the robots I work with. It seems feasible to learn how to correct for this. In fact, this is also what humans do. There is some evidence from the neuroscience community that we humans, we learn a memory of errors to compensate, to correct for errors that we're making. We're learning this memory on tasks, and then this memory helps us correct for errors made faster in the future. So how do we learn to adapt to errors due to changing dynamics? And this how to learn to adapt is this concept of meta-learning, how to learn, how to learn to adapt. And I just want to quickly walk through what it means to learn to adapt from a machine learning perspective. Let's say we have this model that is supposed to predict Y from input X. When we're learning in inverse dynamics model, as I would need for a model-based controller, then this is exactly the same setup. We have a supervised learning problem. We need a loss function. We have some parameters omega here. This loss function computes the error that we're making, and then we're computing gradients to update these parameters omega. So we need to specify this loss function. We need to decide on an optimizer. We need a learning rate, and we also need to initialize this model somehow. And really what meta-learning is all about is it's just really learning all of these things, right? So this is one way of looking at meta-learning. There's a nice recent survey that summarizes these kind of things. So if you're interested, take a look at that one. And just, I don't try to be comprehensive here. I just want to give an overview of that all of these things have already been worked on, of course. So there's, of course, MAML that learns a model initialization. There is some of my recent work of learning, a memory of learning rates that was inspired by this neuroscience paper that I just talked about. There are there's some work on learning optimizers themselves. And then there's also work on learning of loss functions, and this is not updated. This is a paper that we just recently submitted to IROS and that was accepted. So that is what I will be talking about today. Okay, so these are the different ways of doing meta learning, and I'll be talking about this last point here today. Before I go into this, I did want to think a little bit about how meta learning is done, at what levels of what the action space is. And I did notice that most of the work is really up here. A lot of the learning to adapt, meta learning, meta reinforcement learning is all happening up at this higher level. Now, again, I'm not being comprehensive. This was literally me just searching for an hour for related work. And it's very biased by what I know. But again, I think it's true that most people work on this higher level here. And only few people try to actually learn to adapt models that are used by the controller. And I don't know why that is, but I again also curious to hear from you guys why this might be the case. But most of my meta learning work has been at this lower level, and that's what I will quickly dive in now. Yes, so I will focus on the recent IROS paper, learning state-dependent loss functions for inverse dynamics learning. Again, we have this structure here. We do assume the policy is given in this paper, and we're trying to learn the model that is used by the controller. In fact, we're actually trying to learn the loss function that can adapt this model fast. So this controller takes in current joint position and velocity and desired joint position and velocity and outputs torques for each joint. It's parameterized by omega. And really what I'm talking about here is the inverse dynamics model in this controller is parameterized by omega. There is a loss function, like I said before, that we need to adapt these parameters omega. And this is what we're learning here. We use a standard bi-level optimization framework to optimize these loss parameters. So I won't go into the details of this right now, but you can check out our paper for this. There are libraries out there that you can use. This higher library is what we use. And also an important point here is really that our meta training phase is self-supervised, and we use just data from sine motion that we generate on the KUKA arm. So I don't know, anyone who has done system ID on a robot before knows that we often use sine functions on the joints to collect data for this. And that's exactly also how we collect data here. We collect this data, and then we use that sine motion to learn a loss function to adapt the dynamics parameters on those sine motion data. Okay, and now what kind of loss functions are we learning? What we're proposing is to learn a structured loss function here. That structured loss function says that the error made in the torque space should be dependent on where we are in the joint space. So theta is the joint. So this is a weighted loss function where phi j is a little neural network per joint. And it really predicts the weight of how much we should weight this torque error. And why does this make sense? Well, for example, anyone who has worked on the torque level knows that the arms can have like nice little effects like stiction. So when you're around 0 velocity, 0 degrees, for example, on our KUKA arm, it takes a little bit more torque to push through that state, and that is actually being captured with this loss function. There are 3 baselines that we compare to: the standard mean squared error, just learning a pure neural network loss function, and then a weighted loss that is not state dependent. So these are constant weights that we identify here. Okay, so this is kind of the sign motion that we collect. And this is our test scenario. I'm showing the data collection simulation because I don't have the video from the real arm, but we collected this in simulation and on hardware. We do these experiments both in sim and real. I'm just gonna focus on the real hardware experiments today. The test scenario is a pick and place task that we execute, I believe 3 or 5 times, I don't remember, but multiple times basically. And the task in the test scenario is just to adapt the dynamics model as fast as possible to the changing dynamics of this pick and place task. And these are the results. So we have these 5 phases of our pick and place task: reach, lift, move over, place, and retract. And this is our first plot. And real to real means we learned the loss function on the real data and we apply it on the real dynamics of the real system. The x-axis is the time of this specific motion phase. And then the y-axis is the mean squared error that we're making. And lower is better. And our result with our learned structured loss keeps the error really low, so it adapts very fast to the changing dynamics. And we see this result throughout all of the motion phases. And I was super excited about this result. I did expect improvement over the standard just regular losses. And even the just neural network learned loss, but I didn't expect it to be that good, to be honest. So the state-dependent learned loss with a standard SGD optimizer outperforms all other learned losses and also the mean squared error loss. After sharing this initially with the community, we got some questions about what about non-standard optimizers, what about using Adam? And here we see results that are very similar, that even with adaptive optimizers, we still outperform the state-dependent loss used with SGD outperforms Adam with a regular MSE loss. Yes, and we do also have results from sim to real where we learned the loss in simulation and then applied it to the real data collected on hardware. And there, I was hoping to see a little bit more, but here the results are really kind of mixed, and we can see sometimes the learned losses, any of the learned losses outperforming the standard losses, but the state-dependent loss really doesn't buy us anything anymore. And that makes me believe that it is really true that the state-dependent loss, when learned on real hardware, actually does pick up something about how to correct for errors depending on the state on the real robot. All of these stiction things, all of these things that are not modeled in simulation, they are only being picked up on real hardware data. And so the takeaway for me here was that learned state-dependent losses can outperform the domain invariant standard losses if we learn on hardware data. And interestingly here in this scenario, the learned losses, they can transfer to out of the distribution meta test scenarios, which is something that we don't see a lot in meta learning setups where meta train and meta test tasks usually are drawn from the same distribution. We didn't do this here and still our learned loss transferred. So I'm also very hopeful about this. And that was kind of the research part that I wanted to talk about. And then I just wanted to get back to this question of where should we be adapting for the dynamics? I mean, I'm clearly firmly planted in this area right now, down here, but I'm just curious to hear if anyone has any thoughts about what the point would be of adapting the, the policies to the dynamics of let's say, picking and placing an object. And finally, I want to just also thank all my collaborators that I've recently worked with. That's it.
Thank you. I think we have time for 1 or 2 questions.
We have, yeah, go ahead.
Sorry, I was also gonna pick up that question from the Q&A. So,
Oh yeah, just go ahead.
Okay, so there's a question from the audience on, do you think the loss function can be dependent on the velocity as well, instead of only a state?
Yes, it can be. I mean, it's we're super flexible. We can change it. So I'm trying to remember if we made this test. I don't remember right now, but we definitely have thought about this as well. Yeah.
But you don't have results yet?
No, I don't remember having results for this right now. Yeah.
Okay. I have maybe another question about your question, or maybe an answer. So if you have torque sensing at your joints, or maybe at the end effector, I think that makes sense to adapt in the controller. But if you don't have that sensing, then maybe it makes sense to do it in a policy. Or if you take the, yeah, I'm basically wondering about that. Like, how much is that decision on which level you do that driven by what is included in the state feedback, basically?
I agree. It might be a factor of the robot that you use, whether you even have a choice, right? I guess I wonder if you do have a choice, would you still say we should be adapting to the dynamics at the policy level? Because you're forcing your policy to learn about dynamics, right?
Yeah, I mean, I would, if you have that. I guess I'm wondering if it does compensate for the dynamics of the robot arm, though, right? Or sorry, at the arm level to do the trajectories. How do you see? How do you see that working if you, for example, interact with objects that are not attached to the robot, right? Or where you have under actuation, or you try to interact with objects in the environment, that not through holding it, but actually by, I don't know, pushing it around or something.
Right. So I think first I want to make the distinction that even, oh wait, let me try to go back here. Even when I talk about the separation between policy and controller, the controller itself could be a learned policy, right? That just takes the desired end effector or end impedance, and then is some learned policy that outputs the torque. So I just want to make this distinction. I think what I'm just advocating right now for is this sense of modularity, where you have a higher level policy that, given the task, this is the desired end effector position and maybe forces that I want to apply. And then we have a lower level policy that takes that and then, given the dynamics of the task, outputs the right torque, right? If you do choose to do torque control.
Okay.
So I taking on that comment, I think the combination may be the most successful way, although it's the most complex dynamical system. But I guess if you think of, or try to be introspective of how you would pick an object, you as a human, and I'm really talking without knowing, but just from intuition, if I see an object, it could be that I have a first, let's say, policy action of how do I think how heavy it's going to be. And I know that because if I think it's going to be very heavy and then it's suddenly very light, then I have kind of like a queer motion at the first step, but then very quickly my controller reacts to that. So I guess there is a combination of both, where you have a first policy driven dynamics of how much force or how much effort are you going to need for an action, but then very quickly a controller loop that actually compensates for any deviation that you could have on your prior about how much dynamics, how much force is necessary for this task. And I guess, yeah, I think the combination is what makes our interaction so robust. I think if you only do one or the other, the policy is going to sometimes fail in thinking what is going to be the dynamics necessary to interact before it has interact and knows what the dynamics are. And if it's very off and there is no prior, then the controller is going to suffer to kind of like take all the kind of like work on just having, I don't know, a desired trajectory without knowing how much force is necessary for that. So I guess this classical feed-forward feedback is key.
I think you make a good point. There was one of the things I didn't know about, but Chris Atkinson's long paper revealed to me is that in the 80s, they did an experiment where for specifically for a pick and place task, they had humans pick up different loads and then checked how they would whether they would follow the same trajectory or not. And they actually show exactly that the trajectory they're following does not depend on the load. Instead, there is something compensating internally for the load, so they would still follow the same velocity profile. And I found this interesting. I don't know how to generalize this to contact-rich tasks, but it just seems to indicate there is, at least for us, there seems to be some separation of the higher level action spaces and then the lower level like muscle activation for this.
I have maybe one more question. So is it always clear where you draw the line?
No. It was more of a thought experiment how I would do it, and also to force this question of where should we adapt. But I agree also. I think what Roberto says is right. Maybe we shouldn't try to draw this line. Maybe it should be like a hybrid thing. But I do think we should understand why a hybrid thing is maybe useful, and yeah, how should we combine these things? Yeah.
Right. Thank you, Franziska.